Okay, welcome all. We spent half a semester talking about graphical models and half a semester talking about neural networks. And the question was, will they ever come together? And today they will at last. So today is all about structured learning of combinations of graphical models and neural networks. So first, why would you want to do that? I have figures from two papers here to argue that this is actually a worthwhile endeavor. The first one here is from a paper called Deep Lab, which was the winner in the city, or the leader in the Cityscape benchmark in 2016, I think. And they show an example input image and then the output of a deep neural network before and after using the softmax function. So the top row here is before, the bottom row is after softmax, and these are false color maps where they show the activation for the airplane class. So the top row is quite interesting because you see that if we just look before the softmax at the neural network's guess of where there is an airplane, this is actually a pretty diffuse thing. And it's just through the help of the other classes that the contours of the plane come out more clearly. This is the thing at the bottom. And then it turns out that if you then post-process these images with a conditional random field, and here these are several iterations of the inference scheme, that the final segmentation gets better and better. So after 10 iterations, we have a perfect output, and this is of course a cherry-picked example to show that it's a good idea to use a graphical model on top of a neural network. Now, in this paper here, there was the neural network, and then there was the Markov random field or the conditional random field, and these were not trained jointly. So in this paper, only the neural network was trained to do as good as it could, and then I'm not sure how exactly the parameters in the conditional random field were adjusted, but in any case, these two were not trained jointly. And given the success of this paper, there were a number of successors, so several labs in the world had the same idea at the same time. And I've here picked which probably became the most famous of these papers, called Conditional Random Fields as Recurrent Neural Networks. And I think it's a well-written paper, especially the related work section, I think is quite good. And here you see for a few images the output of just a neural network, then a neural network followed by a conditional random field, and here really the combination that was trained jointly, where the neural network has learned what is going to happen with its output and could adjust its predictions accordingly. And again, these are four cherry-picked examples where we see that the result of training jointly is better. Maybe more convincing than these figures are the numbers, so I'm taking them from the paper. The average accuracy here of just a neural network would be 61.3. If you put the CRF, the conditional random field, on top, you get 63.7. And if you train them jointly, That gives you 69.6. And then if you enlarge the training set, it gets better still. So using a CRF for post-processing helps, and then training the system jointly end-to-end really gives you here a big jump in performance. And this is the motivation for me why it's worthwhile to talk about this combination, and to be not completely generic today. So let's just assume that we have a conditional random field with unary and pairwise potentials. So I'm going to say that my entire energy depends on the labels given some input and parameters, and I'm going to make this a combination of unary and pairwise energies. Just as a reminder, what do these look like? So the unary, if I have, so let's see here, my case study is going to be a grid-shaped CRF with pairwise potentials. So the unary energy here is just a sum over the potentials that I get from the individual sites or individual pixels that depend on the label at pixel I given the input and given parameters θ1. And similarly, I have energy for the pairwise potentials. Which depends on the labels at I and j, conditioned on the input and depending on a set of parameters θ2. And a picture that we have often painted is the following. So these are my random variables. And then in a vector graph, if I manage to change colors, no I don't. Okay, in a vector graph, I can indicate these unary potentials like so. And pairwise potentials like so. So this is the picture that we had many times. And now when we want to make predictions, we can either take into account only these unary energies, in which case we would treat all pixels independently, and that is called flat or unstructured prediction, or we can have these cliques, which couple the predictions at individual sites, and that is then called structured prediction. And at train time, it looks as follows. And this is an equation that we've seen before. So I'm looking at a loss. To avoid messing with indices here, just pretend I have a single training example. We're looking at the empirical loss here. We have some ground truth output y, or some maybe I should write T for target, as I've done before. And then we have an optimization process, which can be approximate or exact, which asks for the set of labels, the configuration that minimizes this energy. Okay, and here, if we just look at this part here, if epsilon consists of if my energy here consists only of these unary contributions, this is called flat or unstructured prediction. And if I have pairwise or higher order terms, this is called structured prediction. And now at train time, I'm trying to find parameters which will minimize this loss, where I can also have some regularization term. And correspondingly here, if my energy only consists of, if my energy is simply a sum of independent contributions here, then this would be called flat or unstructured learning, or just learning, whereas if I take the pairwise contributions into account here, then this would be called structured learning. And when I taught a course on machine learning, computer vision 2 years ago, I would have talked about the struct SVM here, and nowadays with the neural networks being so much more powerful, we need alternatives, and it turns out that it's actually not so, it's maybe even simpler conceptually to do structured learning for these systems here. So if you want to build a system, the easiest thing and the thing that you would try first is to just train your unary terms. This is something that you did, I believe, in your first exercise this semester. You simply trained a classifier to predict the right class in each pixel in a semantic segmentation task. Yeah, it's as easy as that. You did not worry about the pairwise terms. That's still useful to get a good initial guess for the parameters, because this can, of course. So nowadays, this would be a neural network if you have enough training data and a GPU. And this could be a parametric function if you don't have so much training data. Or it could also be a neural network. You have used a parametric function before in the exercise that you did here. A neural network in this case would modulate this interaction conditioned on the image content. So in the exercise that you did, you were looking at the contrast difference between two pixels. And you said that if there is a large contrast between two adjacent pixels, then you will not penalize a label transition. But if there is no contrast between two pixels, then you will penalize a label transition. You want to encourage the labels to be the same in those two pixels. Okay. Good. Now, why would you want to go beyond unstructured learning at all? What are the advantages of structured learning? An immediate, obvious advantage is that you can take these interactions into account. So if the neural network knows that a conditional random field is going to operate on its output, and if it understands how this conditional random field, so what effects this has, then during, well, understand is a big word, but it can be trained to produce an output which, combined with the conditional random field, will do well. Okay, that's what I mean by saying take interactions into account during learning. And secondly, now this minimization here, this can be exact or approximate, and especially the approximate optimization schemes, they may have artifacts. But if we use those artifact-ridden inference engines already at train time, then ideally the system can learn to compensate for these artifacts. So let me say that each of these approximate optimization algorithm has its own peculiarities or idiosyncrasies which can be taken into account. Into account at train time or during learning. Do you have any questions so far? Yeah?
What will be the input into the neural networks? Because neural networks only accept the images. So how do we generate the input?
So the neural network in semantic segmentation, the input is an image and the output is also an image.
We combine with the markov random field in this case. So.
Yeah, so the neural network, let's say, if we have 20 classes, the neural network produces an output image with 20 channels, and in each channel it says how likely is this pixel to belong to this specific class. And these 20 channels can be interpreted as energies of these unary potentials. So if it's if a pixel has a large probability of being airplane, then I can translate this to airplane has a low energy at this pixel.
And we use this output to process as an input of this neural network's output into the markov random field.
So the neural network gives us these potentials. Yeah? So the simplest case that we can have is that, let's say this is here pixel number 3. The simplest Markov random field that I can have is just for foreground background segmentation. Yeah? So I could say psi3 for z3 background class has some energy. I'm inventing this. Let's say the energy is 13, and psi3 of z3 being foreground has a different energy. Maybe the energy here is just 4. So this pixel would prefer to belong to class number 1, to the foreground class. And then I have these pairwise potentials, for example, psi 3, 4, which tells me about the interaction between pixels 3 and 4. And this would be a table with 4 numbers or 4 energies. Yeah? So one energy assigned to each possible combination of labels. Okay? And at the very simplest level, my neural network will just give me these unary potentials, but then I could also train a network to also give me these pairwise potentials, which will depend on the local appearance of the image. More questions? Okay. Yeah?
At the beginning, we also had this exercise where we combined a random forest with a conditional random field. This is basically the same idea, just replacing random forest with logarithmic.
Yeah, exactly. Good. So let's make this a bit more concrete. And we're going to look at a couple of different cases. Let's first say that our variable space is categorical. So for example, semantic segmentation falls in this class. And I'm going to show you two approaches here. And both are summarized in a fantastic paper by Justin Domke. It's called Learning Graphical Model Parameters with approximate marginal inference. There's a lot of information in this paper. It's quite dense, but it really gives you a compact description of what's happening. Yeah? And in this paper, Justin Domke looks at two alternatives. One is to use belief propagation as inference engine, and the other is to use mean field iterations. And we start with belief propagation. So as argmin engine, we're going to use Loopy belief propagation. So to remind you, in lecture number 4, we were talking about dynamic programming on chains of random variables, on chain structured graphical models. We argued that the same works on tree-shaped graphical models, and this resulted in a belief propagation algorithm. And I said at the very end that, so let's look again at the rules here. We pick an arbitrary root node, that's step number 1. Secondly, we send messages from the leaves. If the leaf is a variable, its message is a vector of zeros. If the leaf is a factor, a unary factor, it sends a vector of potential values. And then each node waits until it has all incoming messages except one, and then it sends a message along this one remaining link. And we have two types of messages. on the one hand, messages from factors to variables. That's the first line in the box. And secondly, messages from variables to factors. And maybe we start with the second step here, messages of variables to factors. You see that it's just a summation of incoming things. Yeah? So if I show this graphically, we have here a summation of a few inputs, and then we're sending this as output. And of course, I show this picture here on purpose to stress the similarity with what's happening in a perceptron. In other words, we know how to do backpropagation on the second line. And the first line is not much more complicated. Again, we have summation over incoming terms, and then we have something which I could call a bias term. This is the contribution here from the potential associated with the factor itself. And then we have a nonlinearity, namely a minimum operation, and then it sends its output onwards. Okay, so again, this looks very much like a unit in a neural network. And I said that this same algorithm can be used on loopy graphs, but on loopy graphs, we never have all the messages that we need to send the correct message onwards. So in loopy graphs, we simply guess some of the messages and then send ours onwards and continue like this. And usually you try and do this until convergence. But, you know, since it's approximate anyways, you can say, for example, well, let's just do 3 iterations of this. And yes, I know it's not going to be perfect, but since I'm doing structured learning, my neural network can try and make up for the deficiencies of using just 3 iterations, for example. So I can simply use loopy belief propagation for a fixed number of iterations, formulate that as a neural network, and do backpropagation over it. And this is already the basic idea. Okay, so back to today. So we're looking now at categorical variables, and we're looking at loopy belief propagation with a fixed number of iterations as inference engine. And you know, just to give you an example, you know, I'm using a tiny graph which is not even loopy, just to be very explicit here. Okay. Let's say this is my graphical model. And if I now do loopy belief propagation, I introduce a kind of pseudo time here, and I have a node here corresponding to my factor. Let me use a different color to say that, you know, this is now a different picture. This factor sends a message to the closest variable. The variable sends its message to the closest factor. The factor sends its message to the next variable. And at this point, we are, for this variable now, we already know it's marginal. Now we're going to propagate messages in the opposite direction to here and to here. And then we know the marginal at the second variable. So, well, maybe it does not look like a neural network to you. So, you know, in a real neural network, or in the more traditional neural networks that you know, we would have, you know, dense connections here, maybe between 2 layers. So I hope you see where I'm trying to get to. Okay, so the green thing would be a dense neural network that I'm drawing here, and I just want to show you that these message passing iterations can be understood or can be unrolled as a sparse neural network. So belief propagation can be unrolled into a feed-forward neural network. And we know how to do backpropagation on this network. So I get some output for my one random variable and for the other random variable. I compare this to some ground truth. And if I find that the answer was correct, I don't need to do anything. If it turns out that the answer was wrong, then I'm going to now propagate backwards this information and make adjustments, including, for example, at the unary factor. So if I do backpropagation, I will eventually end up at this node here and will know how to adjust it so as to get better predictions. And my unary factor here, let's say, was the output of a neural network. So my information is backpropagated to this node, and from there it's backpropagated into the neural network to tell the neural network how to change its parameters, such that next time I will hopefully get better predictions.
Sorry?
Yep.
Is there a reason why you didn't draw like the middle arrow to the right? I mean, that's just trying to
Yep.
show that you compare it with the ground truth, right?
Yes. If you look again at the...
Oh, sorry, yeah, it's a factor, isn't it?
It's a factor,
Okay,
exactly. Yeah. If you look at the message, the belief propagation equations, in this case, I would not even have needed this. I would not even have needed this node here, because it's a factor which is just connected to two nodes, so it does nothing but pass on the information it has received. So I could directly have jumped from here to there, but because we previously always had messages from factors to variables and variables to factors, I represented all of them here. And like you said, I'm only interested in my estimates at the variables, and this is why I only connected these two to the ground truth information, which I showed here in red. Yeah? So this is where I can inject loss. More questions? Okay. So this is a very general recipe. Wherever we can use Loopy belief propagation, we can write it as a neural network. We can do backpropagation through this network to train the preceding neural networks that actually determined the factors in the graph on which I did Loopy belief propagation. Very nice recipe. But it's not the recipe that was used in the paper that produced the images that I showed you above. In this paper, a different inference scheme, a different approximate inference scheme was used, namely one that we did not talk about before, a mean field approach. So we still look at categorical variables, but our inference engine now is a set of mean field iterations. The idea of mean field is to approximate some original distribution by a product of marginals. So instead of looking at the true distribution P, we are looking at a product of marginal distributions Q associated with each of the random variables. And then we're looking for those marginals that will give us, under our model, the lowest energy or the highest probability. And you can, there are equations that can be derived for a stationarity condition, and these can be used in turn to get an iterative update mechanism that is shown to iteratively improve your estimate. And this is described in brief in this paper by Domke, but you can also read it up in the fantastic book by Koller and Friedman on probabilistic graphical models in chapter 11.5. And the update equation looks like this. We have, so I is here the index of my random variable. L is a particular label. And Z is an approximate marginal that will get out. And here we have a normalization factor on the right-hand side associated with the ith variable. And then in these iterations, we take the unary potential associated with site I and update it as follows. We take a sum over all other sites. We take a sum over all labels in my set of labels. And then we mix in a little bit of the marginal distribution or of the marginal at other sites, and this is weighted by a potential between pixels I and j, depends on the labels I and j and on the observations. So these could be, either the original observations, or it could be some features derived from those. Good, and Ni simply helps normalize the whole thing. So it's a sum over L here. Now, a few years back, there was an influential paper written by Krähenbühl and Koltun, which really combined a number of clever ideas that were already around in the literature. One idea was to use this mean field update equation, and another idea was to choose a particular form for the potential which allows to evaluate this efficiently. And they suggested the following. They said, let's take a compatibility function between two classes L and L prime, and let's use a Gaussian kernel that depends on how similar the observations at locations I and j are. And in fact, this could either be a single Gaussian kernel, or it could also be a sum of different Gaussian kernels here. And okay, so what does this tell us? It says effectively it makes the marginal at I more similar to the marginal at j if they have similar appearance or here, because it's written in a label-wise fashion, for a given label, it makes this specific entry in the marginal more likely if appearance is similar and if the classes L and L prime are compatible. Okay, and after the break, I will give you well, not a full derivation, but a hint at why this can be done efficiently if and only if k is Gaussian, and if these arguments are have a dimension which is not too high. So this works well for a dimension less than 8 or so.